All right, so it was x minus 2 squared, x minus 4, x minus 6 over x plus 3, x minus 2, and x minus 4 squared. All right, so we said before we make any decisions about wholes or vertical asymptotes, like anything, you have to see if you can simplify it. You can cross out the x minus 2. There's 2 in the top, which means there's still 1 left. But we crossed it completely out of the bottom. When you cross it completely out of the bottom, that means there's a hole. So the hole comes from setting this equal to 0. So my x on my hole is 2. Then the x minus 4 cancels, and it would cancel with one of the x minus 4s in the bottom, which means there's still an x minus 4. So the hole is not at 4 because there's still an x minus 4 in the denominator. Does that make sense? Only when we cancel it out completely. So my updated function is x minus 2, x minus 6, x plus 3, and x minus 4. This time they asked about the hole, but they could ask about vertical asymptotes, horizontal asymptotes, slant asymptotes, zeros, end behavior. Like all that stuff can come from your rational functions. So once you simplify it to get the y coordinate of the hole, I take the x coordinate and I plug it back into the updated form of my function. So it was 2 minus 2 times 2 minus 6 over 2 plus 3 and 2 minus 4. And you'd get 0 times negative 4 over 5 times negative 2, 0 over negative 10, which is 0. So that's how I know the coordinate of the hole. The x comes from what you crossed out. The y comes from plugging it in after you simplify. Now let's talk about vertical asymptotes. After you simplify, vertical asymptotes come from your denominator. So there would be 2, x equals negative 3, and x equals positive 4. That's where your vertical asymptotes would happen. Horizontal asymptotes come from looking at the exponents in the top and the bottom, right? In order to figure that out, you don't have to FOIL this out completely, but you would have to know what your degree was. If I had an x times an x, that means my numerator in the top is x squared. And if I had an x times an x in the bottom, it's also x squared. Remember, there's 3 rules on horizontal. If the one in the top is bigger, there is no vertical asymptote. If the one in the bottom is bigger, then the horizontal asymptote is at 0. And if they are the same, it's the leading coefficient of what's on the front of these. This is a 1 and a 1. If I had multiplied this by this and this by this, they would both just be x squareds. If there was like a 2 here, now my numerator in the top, or my highest degree in the top, would be 2x squared, which would be important if it's the leading coefficient. So now that tells me there's a horizontal asymptote at y equals 1 over 1, which is 1. Okay? Questions? Remember, end behavior, the ends in both directions come from horizontal asymptotes. If there's a horizontal asymptote, then as my limit goes to the left or it goes to the right, it approaches the horizontal asymptote. So in both directions here, my limit would have been at whatever, h of x, f of x, I don't know what the function was, equals 1, whether it's going left or it's going right. Yeah. Slant would be if the one in the top is 1 higher. So if it said like x to the third over x squared, something, something, now you have slant. It has to be 1 higher in the top, and you find it by dividing it. So I divide the top by the bottom. That time I'd have to use long division, but if it was like squared and x in the bottom, you could use synthetic. And the exponent.
So that means that
there is
a horizontal.
Correct. You can't have slant and horizontal. It could be neither, but it can't be both. And when we divide, we ignore the remainder. We divide and we just disregard the remainder, and it would be in y equals mx plus b form, whatever you get.
So if it was a 4 in the top and a 2 in the bottom,
There would be no slant or horizontal.
When is the horizontal?
If the one in the top is less than the one in the bottom, or the one in the top is the same as the one in the bottom.
And then when is it vertical?
Vertical just means there's a variable in the bottom. So vertical comes just from the bottom. After you simplify it. Usually there is vertical and horizontal, or vertical and slant. Yeah. Yeah.
Is there like slant and behavior?
So when you get a slant, you would literally have to know what happens at the. So if there's no horizontal asymptote, which would be a case where there's slant, then this is where we took. So let's say it said x to the third. Let's say 2x to the third plus 3x plus 1. I don't know, something stupid like that. And then in the bottom it said x squared minus 1. Let's just say that, right? This is a great question, guys, because it doesn't come up, I don't think, in here. If your Horizontal asymptote does not exist, which would be here, right? That one on the top is less than is bigger than the one on the bottom, so no horizontal asymptote. Then you have to find it by, you grab the leading coefficient, which is the one with the biggest exponent, and you put it over each other. Do you remember this? And then you simplify it, so I would cross out x squared, I end up with 2x. And to find left-hand behavior, I plug in negative infinity. To find right-hand behavior, I plug in positive infinity. You remember that? Yeah, okay. That's if there's no horizontal asymptote. If there is a horizontal asymptote, then your end behavior is the horizontal asymptote. So this one, if I plug in negative infinity, I get negative infinity. So it would be as f of x, or no, as the limit of x approaches negative infinity, f of x equals negative infinity. And if I plug in positive infinity, I get positive infinity. So the limit as x approaches positive infinity, f of x would equal positive infinity. So it would be different, let's say if this was like 2x to the fourth over x squared. When I simplify that, right, I get 2x squared. If I plug in negative infinity, it becomes positive infinity. If I plug in positive infinity, it stays positive infinity. So that's one in which both ends would go up. Yeah.
What are the scenarios where it's like two, like negative and then the two positive when you're going left and right? Like, does that make sense?
No.
You put like the two and it's like x.
Oh, so if you're approaching a hole, so like let's say you have a hole. Let's say I have a graph. I don't know, I have a graph, right? And this one, actually, let's use this example. That had a hole at 0, 2, right? 0, 2, there was a hole. So let's say my graph did this, right? And then it went like this. But I had a hole here, right? So if it wanted you to express the hole in limit notation, that's, or you're approaching the vertical asymptotes, you would use that. So if you're not doing end behavior, you're going towards a value, that's when you get the minus and the plus, the little subscript. That's what you're talking about, right? So this would be the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. Both of these end at the y coordinate of your hole. So this would be f of x equals 2. I think I reversed this, right? Let's just say the hole was at 2, 0. But let's say the hole was at 0, 2, just for, so it makes sense for this. Then as I approach 0 from the right, it would also be 2. So that's how you would express the hole in limit notation. The other thing you could see is if there's a vertical asymptote, let's say there's a vertical asymptote at 3. It could ask what's the limit as x approaches 3 from the left, and it could ask what's the limit as x approaches 3 from the right. For this graph, as it comes to 3 from the left, it would be positive infinity. As it comes to 3 from the right, it would be negative infinity. So for those, you'd have to know what your graph looks like. You'd have to figure out where your vertical asymptote, which happens sometimes. You had to find your vertical asymptote and then figure out where my curves are. You could use your zeros to find that. You could plug in points to find that. Okay, if you had a graphing utility, you could graph it and figure out which direction it's going. But your graphing utility will not show you your vertical asymptotes, so you'd need to know where they are. Okay, that was question 1. Any other questions on 1, 2, or 3? Out of our 28 questions. Okay. So I'm going back up to this question because we just talked about x minus 2, x minus 6 over x plus 3 times x minus 4 is what it looks like after you reduce it. And to find your vertical asymptotes, we set the denominator equal to 0. So in this case, my vertical asymptotes would have been at x equals negative 3 and x equals positive 4. How about horizontal asymptotes? How do you find horizontal asymptotes?
The highest exponent.
The degrees in the top and the bottom. So to get that, I'd have to know that x times x would give me x squared, and x times x would give me x squared. The 3 rules on horizontal asymptotes, right? We use an n for the numerator exponent and an m for the denominator. That's the highest exponent. If n is greater than m, then there is no horizontal asymptote. If n is less than m, then it's at y equals 0. And if n equals m, then it's the leading coefficient in the numerator over the leading coefficient in the denominator. How do you find the zeros of a function? Good. Numerator equal to 0. All right, for 3, well, first of all, the concave up and concave down determines the point of inflection. Changes from concave up to down or vice versa. So if you look at your graph, the U and the N is what you're looking for, and it changes at point C. For 3, you're talking about, now it's not a rational function, right? There's no like variable in the denominator. I don't have to worry about my asymptotes and stuff. So these, to me, these are easier. You're just doing your end behavior on your higher degree. The rule is that you're looking at the highest exponent. So in this case, we're looking at negative 3x to the 5th. If the exponent is even and the leading coefficient is positive, so it's a positive, this would be a positive a to the even power, something like that, okay? Then both point up. So the limit notation on both sides would be towards infinity. If it's even, but the leading coefficient is negative, so it's a negative a to an even power, or x to an even power, whatever, then they both point down. So if I was talking about limit notation, they would both be going to negative infinity. If the exponent is odd, one goes up and one goes down. If it's a positive x with an odd power, then it falls left and rises right. So my limit notation would be it goes to negative infinity on the left and to positive infinity on the right. If it's negative x with an odd power, then it rises right and falls left. So my limit notation would be to positive infinity on the left to negative infinity on the right. To me, that should be an easy question. You just have to remember those little rules, okay? All right, questions on 4, 5, or 6. So 4, now we're in our dilation. So this was our vertical stretch, shrink, all that stuff. So if you remember, if I have f of x equals, the first thing is your positive or negative, and then you had an a, and then you had f of, this could be bx minus c plus d, let's say. So all those little parts, right? The positive or negative on the front does what? Reflects it, right? Over what? Over x-axis. So if it's positive, it doesn't, but if it's negative, it reflects it over the x-axis. What does the A do? Say again? Oh, not on a sinusoidal. It kind of still works the same, but this is a vertical stretch, which they call dilation, okay? By a factor of A. We don't do anything with A, we keep A, right? So if it's at 5, that's a vertical dilation by 5. If it's at a 5th, it'd be a vertical dilation by a 5th. Yeah.
Let's say if we get like a free response like this, we can't say vertical stretch.
I don't think you're gonna, but I think it's looking for dilation.
And then you have to say by a factor of.
By a factor of, yep, for sure. Okay, then inside your parentheses, like this could also be plus or minus. What happens if the B has a minus on it? Good. This would be a negative, would be a reflection over the y-axis. So it flips it left to right, okay? It also changes your horizontal shift, right? If I was going to the right, I would then go to the left. Okay, the B does what? Good. And this time? Good. Horizontal dilation. Factor of 1 over B. So if B is 2, then it's a horizontal dilation by a factor of 1. Oh, what did I say 2? It would be 1/2. If it was 1/2, then it's a horizontal dilation by a factor of 2. So you might see these where it literally just gives it to you and you're describing it in words, like multiple choice in words, but it also might give you a graph, which is what this did, where you have to physically adjust those points. Remember, if it's like a horizontal dilation, we take the x values and we multiply it by 1/2 or multiply it by 2, whatever it is, and we move them. If it was a vertical dilation, we adjust the y values, okay? All right, then C is inside your parentheses. Now, this is where I think it gets confusing with your sinusoidal and these, because on your sinusoidal question, if you remember from your FRQ the other day, this sign was a plus. So your C in your translations, you take it out as the opposite. The effect is the same, but how you state it is opposite. So that, I think, is where it gets confusing for people, okay? So if this was a minus C, if there was minus 2, which direction would you go? You would go to the right. So if it's a negative, we go to the right, and if it's a positive, we go left. But the C itself, you would say, like if it said minus 2, in these, you would say the C is 2. You would have to describe it as moving to the right 2, but C itself is 2. Does that make sense? Sinusoidal, it's the opposite. Sinusoidal, it says x plus C. So if this said x minus pi over 2, then your C is minus pi over 2.
So that's how you would state it.
Correct. So it's always the same direction. Like if it's minus, you always move to the right. If it's positive, you always move left. But if it actually asks you for your C value, which it never did in translations, but it did in sinusoidal. In translations, you would want to describe that. That would be a shift to the right, pi over 2. But in sinusoidal, C is negative pi over 2. Does that make sense?
Yes.
Okay. All right, now D, the last one. Vertical shift, positive up, negative down. So we had questions like these where it asked us to adjust a graph. It asked us to describe the transformations. It asked us to adjust domain and range. All of those things could show up. It asked us, here's a coordinate point. What happens to those coordinate points if you're given like a T-chart kind of a thing. So all those things would be related to the transformations. So in this, when we adjusted domain and range, right? Like number 4, you adjusted your domain and range. 5 is now talking about your zeros. So now you've got zeros in multiplicity. What happens if a 0 occurs an even number of times? It bounces there or touches and turns around, that kind of verbiage, right? Okay. And if it's so in example 5, you had to factor it. It was factoring by grouping. Once you factor it, you got x minus 3 times x squared plus 4. X minus 3 produces 3 as a 0. X squared plus 4 would be 2 non-real zeros. It'd be 2i and negative 2i. So when it asks you to describe them, distinct means by like only one of them, right? So it has exactly one real 0 and it had 2 non-real zeros.
How do you know that it's a non-real zero?
Because you can't factor this, and if I solve that, x squared plus 4 would equal 0, x squared would equal negative 4, and I'd get plus and minus the square root of negative 4, which would be 2i. So as soon as it's imaginary, that's non-real. Okay, geometric sequence was 6. Okay, we talked about it a little bit. Was that yesterday or the day before? Yesterday? Exponential was yesterday. Yes. But for these, when you get 2 pieces of data like that, remember that's like the same thing as having 2 coordinate points. You could look at it that way. But when you set up your your geometric sequence, we do g of the bigger base equals g of the smaller base times r raised to the difference, big minus small. So in this case, you got g of 4 equals 16 and g of 2 equals 36. I would put g of 4 on the left, g of 2 on the right, and then it would be r raised to the difference there, which would have been squared. And then you plug in the values you work your way backwards. So when you find the initial geometric term, it is, in this case it was g, but g of n would equal g1 times r to the n minus 1. And then you have to adjust it based on what you have. So this had g of 0 and r to the n, that's an n. I mean, if you look at your options there, it said geometric, and that was the only one. Well, b is raised to a power, but that was the only one that had a base or a initial term rate times r to the power. So hopefully that was not terrible to pick out. All right, 7 was your semi-log plot, okay? I think we've, like on all the practice tests, I've only seen like semi-log plots 2 ways. One is actually reading it, like could you take something that had data and figure out which one is your semi-log plot, where you're looking for the x-axis to be in even increments and the y-axis to go by 10, then 100, then 1,000, like that. And the other was this, okay? And this I've seen this like twice in the practice test. And all you have to know for this is that if the original graph, which this is my original graph, okay, the x's are going by 20, the y's are going by 200, even increments. So that's your regular graph, okay? And that graph is exponential. If I take an exponential function and I put it on a semi-log plot, it appears linear. So all you had to do is look for the graphs here that were semi-log. This one's not semi-log. This one's not semi-log. These were, but we needed it to be linear. This is the only one that appears linear, okay? Those should be easy questions unless you have no idea what you're doing. All right, 8 was your trig function. So this time you're solving, and in this question was your double angle. You have to know your double angle formulas. Sine of 2 theta. This is all on that like cheat sheet too. Sine of 2 theta is sine cosine. Cosine 2 theta or 2u has 3 options. Cosine squared minus sine squared, 2 cosine squared minus 1, and 1 minus 2 sine squared. You have to know these because they will be built into the questions just like this one is. It says cosine 2 theta there. And then the other side only had sine, so I would have known to pick this guy, 1 minus 2 sine, and then you would have had to solve it. If you look this time, it gave you the natural unit circle, so we weren't adding 2n pi. Don't forget that that could be part of it. Number 9, you would have to know what these graphs look like in order to figure out if they're concave up and concave down. So remember your exponential a, b to the x. If my a is positive and my b is bigger than 1, then my graph points up. So a, positive, b, greater than 1. If my a is negative and my b is negative a, b is bigger than 1, then it flips it upside down. If I have a positive a and b is in between 0 and 1, so it's a fraction, now it's decreasing. And if it's a negative a and my b is between 0 and 1, then it flips it the other way. And then you have to obviously know concave up and concave down. Concave up looks like a U, concave down looks like an N. So when it asks which of these was concave up, A was the only option. All right, 10 was talking about rate of change. You actually had to find your rate of change and compare them. So it wanted to know on which of these intervals was it the smallest. 1 to 2, 2 to 4, 4 to 7, and 7 to 8. This is a question that could take some time. I think that's why they give you a lot of extra time on this portion, because these kinds of questions are time eaters, right? You have to actually find the rate of change from 1 to 2, from 2 to 4, from 7 to 8. And pay attention because these did not go in even increments. So you can't just do it over 1, right? It was 115 minus 53 over 1, but then it was 240 minus 115 over 2, 410 minus 240 over 3, and 468 minus 410 over 1. And then you had to compare them and see which one had the smallest average rate of change. All right, 11 was back to transformations, but based on exponential functions. So it said, let f be the given at 4 to the x. Which of the following would have a horizontal dilation by 2? And that would be your b value, which would be in the exponent on an exponential function, would be 1/2. So then I can separate this out. This would be 4 to the half plus 4 to the x, and 4 to the 1/2 is 2. Oh, and then that wasn't an option. You had to look at it a different way, which was this. You could literally have taken the 4 and square rooted it. So that's how else it could have happened. 4 to the 1/2 was the square root of 4 raised to the x, and that's the option that was there, A. So this would have represented a vertical dilation. This would have represented a horizontal. Okay, so for 8, the first thing I noticed is that this is cosine 2u, so I have to replace it. And of my 3 choices, I only wanted the one that matched this trig function. If that was sine, I mean, if it was cosine on the other side, I would have picked 2 cosine squared minus 1. But because it's sine, I pick 1 minus 2 sine squared theta equals 1 minus sine theta. That's the formula. Then as soon as you know you've got a sine squared and a sine, I know I'm going to get everything to one side. So I can either subtract the 1s, and when they cancel, I end up with negative 2 sine squared theta equals negative sine theta. Now, it doesn't matter which direction I go. I can go right to left or left to right. If I move this over here, 0 equals 2 sine squared theta minus sine theta. And then we have to factor out the theta. Factor out the sine. So sine theta times 2 sine theta minus 1. And then I'd split and solve that. So sine of theta equals 0, and 2 sine theta minus 1 equals 0. So go back to your unit circle, right? Like, where is your y 0? Your y would be 0 here and here. So that's 0 and pi.
So sine theta equals 0.5.
And then, that one you'll solve. 2 sine theta equals 1. Sine theta equals 1/2. And then the coordinate point that has the y, that's a half, is your over 6's. So your over 6 in the first quadrant, where all students take calculus, would be important, obviously. I know sine is positive first and second quadrants. So I want the over 6 in both, which is pi over 6 and 5 pi over 6. And then all 4 of these are your answers. Now, I gave you the interval, but remember, if it doesn't, you have to add on 2n pi. Like, I would have had to say each of those plus 2n pi if it didn't give me the interval. Hadley.
Why do you add the 2 into the minus sine?
Because that's the formula for the cosine 2 theta.
Oh.
Yeah. All right, 12. You had to first simplify. So this is an identity. Cosine over sine becomes becomes cotangent. And then you had to know what cotangent looks like. Of your 3 options there were only 2 cotangents. Of your 4 options. B and D were cotangents. So then the next thing you had to look at was the period on it. So if it was cotangent of pi theta, then remember the period. So period for sine and cosine are 2 pi over b. The period for tan and cotangent are pi over b. You had to know that to differentiate between B and D here. Honestly, if you couldn't remember that, you should at least be able to know cotangent goes up, left, down, right, and then you can narrow your choices down to 2 and make an educated guess. All right, 13. The table shows the function. This was very similar to what you did the day before yesterday. It says, what is the value of f of negative 1? So of 1. So f of 1, we go to the chart, we see that that's negative 2, and then f of negative 2 was 3. To me, this is an easy question. You just understand composite functions. All right, 14. This time it said an amphitheater has rows that are in the shape of an arc. The first row contains 14, second contains 17, third contains 20, and so on. You had to identify that those were increasing by 3 each time, which makes this an arithmetic or a linear function, right? And then it said how many rows of seats are there if the last row contains 50. So arithmetic is if you're adding or subtracting the same thing each time. AN equals A1 plus D times N minus 1. So in this case, you knew that it started at 14. We went up by 3, so it would have been 14 plus 3 times N minus 1. And then it wanted to know how many rows of seats are there if the last row contains 50 seats. So we would have set it equal to 50. And then solve from there, and you would have gotten that it's the 13th row. You could have also plugged those values in.
For the other formula for geometric,
Yeah.
it's AN equals A1
Times R to the N minus 1.
to the,
Yep. Okay, 15 combined again, the double angle. So your double angle formula was there again. That's already twice that's on there. And then you had to simplify it. So and this could be on an open-ended question. This could have been built into your FRQs. It probably would have said something is rewrite this function in terms of tan. And then you would need to know that you're going in that direction. But that would be fair game for multiple choice without a calculator, or the FRQ without the calculator. 16 was the period of the function. So how do you know that it's the period? How do you know where a period starts and stops from a graph? One full complete shape, right? So this didn't happen until it was from 1 to 5 was where your shape went. It went up and then it came back down again. You had to get to the point where it came back up again. Again, that should be like an easy question. Takes 15 seconds. That stuff should be easy and time fillers. Yeah. 19, you're back to your rational functions. So now we're at 2 questions for rational functions. This time was about your vertical asymptote. You had to factor, see if it would cancel, and it did, which means it affected the whole. What was left was x times x minus 2 in the denominator, and that gave you 2 vertical asymptotes. All right, 18, now you're talking about converting from polar to rectangular. This is actually, I know some of you are helping the advanced kids. They're currently doing this. Polar to rectangular means you have r theta and you're going to xy. So remember, this is r cosine theta, r sine theta. That's how I go from polar to rectangular. To go from rectangular to polar, so I'm going from xy to r theta. R is the square root of x squared plus y squared. And tan theta equals y over x. So we inverse tan that and use location of original coordinate point to choose the theta. All right, 19, like if you don't get questions like 19 right, I should be able to beat you with your own iPad. I mean, seriously. If you don't know your unit circle by now, for the love of God, learn it, okay? And we're going to use this as a good segue. I'm going to stop here. Tomorrow we'll pick up with 20, and we're going to do some practice.